Hi, my geometry loving friends. I hope y'all are doing well, and we're jumping into our Saxon Geometry book, and we're jumping into lesson 48. Sorry, I forgot to put that on my board. So lesson 48 is where we're jumping in at this week. Now, it sounds a little odd what we're starting out with. We're starting with indirect proofs. So typically we do direct proofs, right? If I'm given this and I need to know this, how can I directly prove that? Well, this week we're actually jumping into indirect proofs. So I want to draw your attention to page 315 in your textbook. So it talks about that direct reasoning is a process of reasoning that begins with a true hypothesis, and it builds a logical argument to show that a conclusion is true. Now, don't you wish that everybody did that, right? Unfortunately, we live in a world where not everybody uses direct reasoning, right? They'll say, how do I know the sky is purple? Well, I feel like it, right? Well, that's not direct reasoning, right? So when we're talking about indirect proofs, well, perhaps there's a proof sometime that you can't directly prove by saying because this, then this. Then what you do is you go about it indirectly. So you're assuming that it is false. And then if you can contradict that or show that that's not true, then you could prove it what we call indirectly. So I hope that makes sense to you. So page 315 explains that. It's also called a proof by contradiction. Instead of that logical proof statement, you're showing it's true by contradicting the false. So I hope that makes sense. We're saying the negative is not true. All right. So your book shows an example, and I think it's pretty interesting. I would encourage you to take the time, whether before or after this video. But example 1 on page 315, it talks about if two lines intersect each other. So we know that two lines intersect each other and make a point. Well, could you prove that indirectly? Well, if you assumed that that wasn't true and said, well, two lines won't, and then went about the process. Well, your book talks about how always drawing a diagram of that would be something that would be helpful, because can you prove that two straight lines, now you could have a line loop back around, right? That wouldn't be the definition of a straight line though, would it? So two lines can't intersect each other with more than one point. So even drawing a diagram is going to prove that that statement is true. So therefore, indirectly, you're contradicting it because it can't be the false of it, right? So example 2 shows writing an indirect proof. I thought example 2 was interesting on page 316. So it shows how to write an indirect proof. So they have a picture there in your book, and I hope you guys are taking time at home to look through that. But here's the picture that it shows. Well, you can see clearly that that is a diameter. How do I know it's a diameter? Well, the definition of a diameter, it goes through the center point. It's a straight line. But it says, assume that it's not. And assume that ADC is not a semicircle. So you're assuming that it's not 180 degrees. Excuse me. It says since AMC is a straight angle, and it does go through the center point, and it does touch the vertices, the sides, not vertices on a circle, but since it does touch the outside and it is a straight line, then the arc has to be 180. If that arc is 180, it has to contradict our assumption. ABC has to be 90 degrees because it's a central angle for, it's the angle, since it touches on the outside, and ADC makes 180, half of 180 is 90. So ABC has to be 90 degrees. So it contradicts our assumption, doesn't it? All right. Now there's an example 3 there as well about writing another one. Excuse me. Now let's take a few moments and look at our lesson practice. Lesson 48 wasn't too difficult, was it? Just kind of thinking about proofs in a different light, isn't it? All right, state the assumption you would use to make an indirect proof to show that the measure of angle X equals the measure of angle Y. So if you're looking at it the opposite way, if we're doing indirect proofs, you would assume that the measure of angle X does not equal the measure of angle Y. So good job. All right, letter B. It says state the assumption you would make to start an indirect proof to show that line AB is perpendicular to BC. So if I'm doing an indirect proof, what's the opposite? That it is not perpendicular. So then I would set out to do that. All right, those are the answers. That's all you need to do. Sometimes in geometry, we try to make the answers a little bit harder and think, how am I going to answer that? But that's all it's asking us. It's just asking, how would you set that up? All right, let's look at letter C. An isosceles triangle has at least two congruent sides. That's what makes it isosceles, right? Two congruent. To prove this statement indirectly, assume that an isosceles triangle does not have at least two congruent sides. What case needs to be explored to find a contradiction? Well, there could be more than one way to look at that. So I know that if I'm looking at that, if all the sides are congruent, then it's not an isosceles, right? Then it would. What if no sides had equal? Then that would be another way to prove it, because isosceles has to have two. So those are two cases where it would not be isosceles, and that's what it's looking for. Okay? All right, I'm going to let you finish up that lesson on your own. So it's not a difficult lesson. It's just more coming about it a different way, right? Looking at a different way. Now, lesson 49, I think, is a great fun one. I actually brought some things to class to look at, some geometric solids. So it's talking about introduction to solids. And a solid is simply a 3D shape, right? So the common name would be a cube, right? But the base, it has two bases that are the same, right? And the length, width, and height are all the same, so we call it a cube. Excuse me, friends. I'm sorry for yawning. I need to drink a little bit more of my coffee, huh? All right. I hope you all are wide awake while you're watching the video. All right. Now, your book is talking to you about a solid as any 3D shape, three-dimensional. It has to be closed. Solids can have flat or curved surfaces. So I've got some solids that have curved. So we know this is a cylinder, right? Because the bases are circles, right? Some other curved shapes that I might have is a cone, right? A cone has a circular but a pointed top, right? Now, a fun one is a sphere, right? Because that has no flat edges, right? So that is a solid, right? But it is not a polyhedron, right? How do I know? Because it says any closed 3D figure formed by four or more polygons that intersect only at their edges is called a polyhedron. So a polyhedron has to have all flat edges. So a cone or a sphere is not considered a polyhedron because it's not flat, right? A cone is a 3D figure with a circular base. A cylinder, we've already talked about. A sphere is a set of points that are all fixed. So a common sphere that we think about is a basketball, right? Okay, it asks us to identify the solids below in example 1. They gave us a cylinder. They gave us, let me see if I can find mine like that. They gave a triangular prism, right? And how I know it's a triangular prism is because both the bases have triangles and then it has flat edges coming to it. So a prism is named by its base. So that would be a triangular prism. All right, and then it gives you a cone. Now, look on page 321. It talks about the face of a polyhedron. Now, faces are the flat surfaces, right? and that's important that you know the proper terminology, because we're going to talk a little bit more about some of the terms of these things in a little while. So faces are the flat sides, all right, like bases. All right, then an edge is the line where faces meet. So this would be an edge, edge, edge. So this base has 4 edges, right? Now a vertice, another name for that would be a corner, right? So the corners, how many corners does it have? So if we're looking at this cube, let's talk about faces. I've got the top and the bottom, the base, and then I've got 4 around the side. So I have 6 faces, flat planes, right? Flat surfaces. So I have 6 faces. But how many edges do I have? Well, I have 1, 2, 3, 4. 4 and 4, right? 4 and 4 on each of those. And then I've got 5, 6, 7, 8. So 4 and 4 make 8, 9, 10, 11, 12. So I've got 12 edges. Now, how many corners do I have? Well, I've got 4 and 4 make 8 corners, or vertices, right? All right, so the book is telling us something really interesting about faces, edges, and vertices. If you look on page 322, it's called Euler's formula, and it says you take the number of V vertices minus the edges. So we had 8 vertices minus how many edges? And edges, there were 12. So 8 minus 12 is -4, plus the number of faces, we had 6. So -4 plus 6 is 2. So, and that's Euler's formula, that if you take vertices minus edges plus faces, you'll always get 2. Isn't that interesting? So just a neat little thing for you to do there. All right. And that was on page 322. So you can try that with different shapes. Maybe this one, can you name this? I hope you can do this at home. I'm kind of turning it to the side so you can see what the base is. So how many sides are on that base? Can you see? All right. So it's 5. So we call that a pentagon. I hope you said at home. So since it's a pentagon on top, pentagon on bottom, we call that a pentagonal prism, right? So that's fun to look at different shapes. As long as the bases are the same, we call it a prism, the 2 bases. Now, where some students kind of get a little bit confused is when it comes to a point. So this would be a pyramid, but it would be a square pyramid, right? Because the base is a square and it comes to a point. But we can have different, this would be a triangular pyramid, right? Because the base is a triangle and it comes up. So do you see the difference in these two? Because this base is a square and this base is a triangle, but they come to a point, so that's why we call it a pyramid, right? Because it comes up to that. Now look at the difference with this. This is a triangular pyramid. This is a triangular prism because both ends are. So very interesting to explore those different solids and think through the different names of those. So I really enjoy solids and classifying them. So that's a lot of fun. All right. So your book goes over different terms. It talks about lateral face. A face of a prism that is not a base is called a lateral face. All right. The base of a prism is one of the 2 congruent parallel faces of the prism. So I've got a square prism. Notice that it's not a cube because this length here on a lateral face, which is not the base, these 2 are the base because they're the same. If it were exactly all the same, this is a cube. But do you see the difference? Because this is double the length, right? So we call this a square prism, right? So these would be the lateral faces, and these 2 would be the base. All right. We talked about prisms. We talked about pyramids. All right. Now, it also asks you how many faces, edges, and vertices. So and they solved one, and they also figured out that Euler's formula worked out. Let's jump into a few of our practice on lesson 49, and we're on page 323 is at the bottom, and then we'll move over to 324. All right, so again, we're in lesson 49. Now it says, use the information shown to verify that triangle DEF is similar to MNP. So they've given you two triangles there. They've shown you two angles that are similar. So we know the third has to be, since we've talked before about angle. So we know that it has to be. All right. Verify the information shown. So as we're just talking about that they have to be equilateral just because of angle, correct? All right, I'm sorry. I am actually jumping into your lesson, and I thought, wait a minute, I do not have what's going on there. So I apologize. But anyway, I've already given you the answer for number 1, but you won't have to do that at home, will you? Since angle. But your book goes into a little bit deeper that since I know that angle D is similar to angle M and F is similar to angle P, then the angle similarity theorem applies. So sorry about that, friends. I was going too far. All right, jump back up to the top, to the middle of page 323. Sorry about that. I was so excited to get into your lesson with you, wasn't I? All right, it asks us to classify the solid. Name its vertices, edges, and bases. Well, it's a cone. How do I know it's a cone? Because the base is a circle. It comes to a point. So it has no edges because the base is a circle, right? So let's take a look at my cone. So it's flat here, but it's not, there's no edges here. So it's not a polyhedron since it's circular, right? So it has no edges and it's a circular base. We do know the center of the base is X because of what they've told us. All right, letter B, classify the solid. How many vertices, edges, and bases does it have? Well, let's talk about it. All right, it has to be a triangular pyramid. And the reason that I know that it's a triangular pyramid is because in the book, it shows the base is a triangle and it comes out to the top point P. So the base is MNO and then the point P. Classify the solid. How many vertices, edges, and bases does it have? Well, I switched the wrong one. Sorry about that. I was trying to put up the cone and I swapped it there. All right, so it's got one base because it comes to a point, right? So the base, it says how many bases does it have? It has one base, a triangular base, right? How many faces does it have? Well, it has, the base is 1, 2, 3, 4. 4 total, 3 lateral, and 1 base, right? So 4 total faces. How many edges does it have? 1, 2, 3 for the bottom, and then, we're on edges, right? 1, 2, 3 edges here, and then 1, 2, 3 edges here. So that'd be a total of 6 edges. Now, how many vertices? 1, 2, 3 on the bottom, and then 1 at the top. So 4 vertices. So we've got 6 edges, 4 faces, and 4 vertices. So if we added those up, 4 and 4 make 8. 8 minus 6 is 2. So that was Euler's principle there. So very interesting. All right. How about letter C? Classify the polyhedron. Determine whether it is a regular polyhedron. Remember that regular means all angles and all sides are the same. Now, let's count how many sides it has. 1, 2, 3, 4, 5, 6. So the picture is hard to see on letter C, isn't it? All right, so it is, since there are 6 sides, it's a hexagonal pyramid. It is a regular pyramid, but not a regular polyhedron. Now let's talk about why. because all the sides of the base and all the angles of the base are the same, but it doesn't show any markings on its lateral face coming up. So in order for it to be regular, all of them would have to be the same. All the bases are the same. So the hexagon is irregular, but not the 3D part of it. All right, so letter C. Now, letter D. Don't forget that when you hear regular, if you're on a standardized test, you know all angles, all sides, right? All right. That was it. So it was a regular pyramid, but not a regular polyhedron. All right. Letter D. It says classify the polyhedron, determine whether it is a regular polyhedron. I count the base, and there's 5 of them, so that means it's a pentagonal prism. It is not regular because it has not shown us that any of the sides are the same, right? All right, I'm going to let you finish that lesson on your own. So that is lesson 49. Very interesting. I love shapes. I think that's a lot of fun. So I hope you all are enjoying that. All right, geometric mean, lesson 50. Geometric mean, your book is talking to you about some useful relationships that we're going to see. An altitude is drawn from the vertex of a right triangle's 90-degree angle to its hypotenuse. It splits the triangle into 2 right triangles that exhibit useful relationship. So look at your picture there. Theorem 51 talks about if the altitude is drawn to the hypotenuse of a right triangle, then the 2 triangles formed are similar to each other and to the original triangle. So what's really great there is you can set up proportions since they're similar to each other. Now look at page 328, example 2. They show you how to set up those ratios and to solve them. Now example 3 talks about the geometric mean. For any positive number A and B, you can set up what we call the geometric mean. Now don't forget when you set up a ratio, when I have 2 numbers set up as a ratio, let me show you what that looks like up here. Excuse me while I slide over my chair. All right, so your book shows you that if you have x over a equals b over x, you can cross multiply, and that would be x squared equals a times b, right? So one thing that I want you guys to think through is when we look at these outer ones, we call this the extremes, and these are the means. So the means always equal the extremes. And so we can solve that. So your book shows that they set up x over 3 equals 12 over x. So when you cross multiply, it's x squared equals 36. Then you can square root both sides, x equals 6. It has to, because the means and extremes always equal each other. And that's called the geometric mean. So your book did that for you on page 328. Now they're showing you other altitudes that are drawn and other relationships that are formed there, and how you can set up those ratios to solve each one. And so you've got a couple corollaries there. Corollary 50, 1, 1, and corollary 50, 1, 2. And so as you're solving those, just some neat principles there. It says, if the altitude is drawn to a hypotenuse of a right triangle, then the length of the altitude is the geometric mean between the segments of the hypotenuse. So they solved that there. Look at example 4. They did the geometric mean of the 2 hypotenuses multiplied together where it was divided, and they ended up getting y squared equals 4, square rooting it, y equals 2. And so then you've got 2 sides for each triangle. You can just use the Pythagorean theorem to solve the rest. So that's a great relationship that's formed there. Let's take a look at our lesson practice for lesson 50. And that begins for us on page 330. And it starts out by saying, name the similar triangles. So you're just showing the similarities between those. Be careful, because the hypotenuse of one is not the hypotenuse of the other. So the triangles are kind of switched around a little bit. So you want to be guarded and on the lookout for that. So you could say triangle DEF is similar to DGE is similar to FGE. So don't forget you've got two smaller, but then you've also got the larger, and all of them have a relationship with each other since they're right triangles, and you know the altitudes form more right triangles. So that makes three similar triangles, the larger and then the two smaller. All right, letter B, find the values of X and Y. All right, so again, I can solve this by setting up a ratio, right? Well, I know that the outside is 18. I know the outside large hypotenuse is 30. So I can just use the Pythagorean theorem to solve for y on the outside. So y squared equals 30 squared minus 18 squared. So it's easy to solve for y to begin with. And when you do that math, it ends up being 24. Now, once I know that, then I know some in each of the smaller, right? Because I didn't know anything to the smaller right at first without using that Pythagorean theorem. Now I can set up a ratio. So I've solved for y. All I need now is x. So I've got to set up a ratio there. So what can I do? So x is to 24. So x is to 24 as 18 is to the hypotenuse of all, 30. So I'm just going to cross multiply there. 30x equals 24 times 18. Now, I picked up at Walmart, they had calculators on clearance. So I was so excited. I thought, oh, I'm going to need that while I'm videoing. So I picked that up this week. So I was super excited. I love these scientific calculators. Now, I love graphing calculators. They just cost a little bit more, right? So 30x equals 432. Divide by 30. So what does x equal? X equals 14.4. So now we've solved for y at the very beginning by our Pythagorean theorem, and then we also solved for x. So great job. All right, letter C, find the geometric mean between 4 and 11. Remember, we did that over here. So you're just going to replace that with 4 and 11. So x squared equals 44. And then you're going to have the square root of 44, which is approximately 6.6. Don't forget, you'll need to have the wavy since it's not a precise, perfect square root, right? All right. So I'm going to let you finish that lesson. I don't think it's a difficult one. It's just maybe a little bit different way of looking at it. But neat relationships are formed and you're able to solve these very easily. All right. You do have an investigation in your book of investigation 5. It talks about nets. And nets is simply if I took a 3D shape and I laid it out flat. Have you ever got like a box that you had to put together and it even told you where to glue? Well, it was a net shape of that and you put it back together. So recently I was helping someone move and they had picked up some boxes that were so interesting how they came together. It wasn't like the typical kind of boxes. It had these flaps that you tucked in and then all of a sudden it came with a lid. And it was super fun, but I just thought, wow, that's great geometric shapes there. They were nets, weren't they? Where they were flattened and then just came together to be a 3D shape. All right, last lesson that we're doing is lesson 51, and it is properties of isosceles and equilateral triangles. So you guys, there's such neat things that properties that these triangles have. And it's so important that you learn these because when you're taking standardized tests, if you remember some of these properties, it's going to make some of the test questions so much easier. So remember that if it's an isosceles triangle, that means that two sides are the same. Then that means the angles opposite those two sides are also going to be congruent. So that's important. The bases of isosceles triangle are the same. Now, if two angles of a triangle are congruent, then the sides opposite those angles are also congruent. If a triangle is equal angular, then it is equilateral. So if the angles are the same, then the sides are the same. So that's going to make proofs so much easier if you can hold on to those proofs. Given it's an isosceles triangle, then the bases have to be the same of two of the sides. Given it's an equilateral, then all the angles and all the sides have to be congruent. All right. Theorem 51.4 and 51.3 talks about if a line bisects the vertex of an angle, then it is perpendicular. It is a perpendicular bisector of the base. So they've given you pictures of that there as well. All right, let's look at lesson practice. For the isosceles triangle shown, determine the missing angle. Well, it gives you the picture of an isosceles triangle, and it shows you that 72 is opposite one of the congruent sides. So if that one's 72, the opposite would have to be 72. Let me show you that shape. So it just looks like this. And it says this, and it says this is 72. Well, because that's opposite this side, then also this has to be 72 degrees. So all I need to do is add together 72 and 72, which gives me 144. And then I just need to subtract that from 180, and I end up with 36 degrees as the top. I figured all that out from one side and knowing that they were isosceles, so I knew that two of the bases had to be congruent. So that's a great relationship that's formed there. All right. Letter C, if the vertex angle of an isosceles triangle measures 20, what are the measures of its bases? Well, you just 180 minus 20 is 160. Divide it in half, and that's what it has to be. A triangle is equiangular. Well, I know if it's equiangular, it's equilateral. And its perimeter is 7. Determine the length of each side. I'm just going to say 7 divided by 3, right? Because if its perimeter is 7, all the sides are the same because all the angles were. So what great fun it is when I understand those relationships. Well, I hope you guys have a great week, and I look forward to seeing you soon. This week's lessons, lesson 48 through 51. I hope you enjoy it, and I hope between your indirect proofs and some of the new reasoning of thinking through some of the triangles. Some of that is common sense, but maybe you've not thought through those before. So I hope it's a help to you. God bless you all. Have a great week.